Chapter 2, Discovering the Universe for Yourself. Let's take a look at some of the goals in this chapter. So we want to know, what does the universe look like from Earth? Why do stars rise and set? Why do constellations we see depend on latitude and time of year? So let's take a look. So if you're looking at the night sky with the naked eye, meaning that we're not using any telescope or anything, we would probably be able to see about 2,000 stars as well as the Milky Way. And the Milky Way is this disk shape, cloud shape that you can see in the night sky. Unfortunately, with the pollution that we have in big cities, and the light pollution especially, seeing something like this is extremely difficult. But if you go to, for example, the top of mountain somewhere with less light pollution, you would probably be able to see Milky Way. Not as spectacular as in this picture, but you could probably be able to identify that. We also have constellations, and this is the groups of stars that are in the same location in the night sky. There are 88 of them, and that covers the entire sky. And so, for example, what we have here is just an example. For example, we have an um, Orion constellation, and you can easily identify these in the night sky. There are three very bright stars, especially in the northern hemisphere: Betelgeuse, Canis Major, and Ceres, and they form a triangle. These are very bright stars, and you cannot miss them in the night. And this is called winter triangle. You might also have seen the Orion belt. This is the three kind of close stars that we call it Orion belt. So in this picture, they are close to one another, but in reality, if you're looking at them in the night sky, they should be a little bit further away from one another. But identifying them in a night sky should not be very difficult. So I encourage you, if we have a clear night without any clouds or anything, I encourage you to go out in your backyard and start looking at the night sky. This is something that we are not doing these days, um, because the technology doesn't let us to do anything, right? So I encourage you to go and take a look for yourself. And this should be very easy to identify. Once you have the Orion belt identified, you can find star Rigel. This is also very bright. Betelgeuse, Canis Major right here, which is a constellation as well. And then you have Ceres here. So this is fairly easy to identify in the night sky. Let's take a look at this thought question. And again, I want you to stop the video, read the thought question, and answer it. And I will go over the answer in a little bit. So the brightest stars in the constellations, A, all belong to the same star cluster. B, all lie at about the same distance from Earth. C, many may actually be quite far from one another. And I think the obvious answer is C. So for example, the Orion belt that you can see, and you see him just like a belt, right? You see him like that in the night sky. It's actually three different stars that are relatively far away from one another. But when you're looking at them with a perspective of Earth, okay, you see them in the night sky like that. So they're actually pretty far from one another. They're not even in the same star cluster. But from our own perspective, we see them as they appear. The celestial sphere, it's an imaginary sphere. It's not real. because these stars are really, really far away, we we kind of see all of them and we feel like they're all in the same distance from us. Okay, for example, the Orion belt that I was just talking about it. These three stars, they can be in a different distance from us. The first one could be completely different from this third one, for example, in different distance, different type, but we see them as they are in the same distance because they're really, really far away. And that is called um, the celestial sphere. So we see all of these stars, these imaginary sphere, um, and we see all of these stars as they are in that imaginary sphere. It's not a real sphere. Okay, um, and the other thing is, we know that the axis of Earth is tilted 23 degrees, right? So we know that Earth has a tilted axis. We try to draw it. So let's say that this is Earth, okay? And let's say that this is the axis of Earth, which is now tilted 23.5, 23 and a half degrees, okay? But we obviously don't feel like that. We think that we are upright. We don't feel like we are tilted, but that's the axis of Earth. It is tilted 23 degrees. In other words, when we are rotating around ourselves every 24 hours, once every 24 hours, okay, that's how we are rotating. Okay, so that's the rotation. But the axis for this rotation is tilted 23 degrees, 23.5 degrees. Now, if I want to, if I want to draw where the sun is or where other planets are, I can say, okay, the sun is right here and the other planets they are laying in the same, they're lying in the same plane. Okay? Now, I want you to imagine that. What if I could think that I can remove the tilt axis of Earth, but instead tilt everything else? Okay? So here in this picture, the axis of the Earth is not tilted. Okay? It is upright. But instead, the ecliptic plane, this is the ecliptic plane. This is where the sun path is. This is where the Jupiter path is. This is where Saturn path is. This is where Mars's path is. They're all in the ecliptic plane or ecliptic line. What if I could tilt that 23 and a half degrees? Instead of having the axis of Earth being tilted, I can think that the ecliptic plane is tilted 23 and a half degrees. Okay, in other words, if you are looking at the path of the Earth, sun from Earth, you see something like this. As it's rising and setting. Okay, so it's 23 degrees and a half. Now, this is obviously not the true model because we know that the Earth is not the center of our solar system. We know that sun is at the center of the solar system. Okay, but just from our own perspective on Earth, this is what we see. We obviously don't see that we are tilted 23 degrees, 23 and a half degrees. We obviously don't feel like we are rotating around the sun. And this is what we would imagine. This is what our own perspective, this is what we see. So we see the path of the sun, the path of the other planets are tilted 23 and a half degrees, and we are at the center. That's what we see when we are looking at the night sky. So these 88 official constellations cover the entire sky. Okay, so as long as you have a sky map, you can kind of find your way around. You can say, okay, so this constellation is here, and I'm looking for that particular star, and that star is close to this constellation, for example. Okay, and then you can find what you're looking for. But the important point is that these stars are not in the same plane. These stars are not in the same sphere. This is what we feel because they are really far away from us. That when we are getting their light, it definitely feels like that they're all coming in the same spot. Definitely feels like that they are all having the same distance. And if you're at the center, the ecliptic plane or the ecliptic line here would be the path of the sun. Okay? So the Milky Way, this is, I just talked about it, a band of light that makes the circle around the celestial sphere. So it is not covering the entire sky. It is only a band, a cloud, a disk. But why? And why, if we are in a galaxy, and a galaxy is millions and millions and billions of stars in all random directions, why we cannot see it in the night sky? We only see a band. We only see a band here. And the reason is pretty obvious. So let's say that this is our position, the position of our solar system. If you are looking at this blue arrows, you're looking at if you're looking at these blue arrows, you're either looking at the center of the galaxy or you're looking at some portion of the galaxy. You're looking at a specific point of the galaxy. So you would be able to see that band of um, clusters of the stars. But if you're looking at these white arrows, if you're looking up or down, not exactly toward the center of the galaxy, you would just see a normal sky. You would just see clusters of the stars and a bunch of stars, but you don't see the galaxy. That's why it appears to be a band of light here. So when I'm looking at this, if I am looking exactly here, I know that I'm looking at either the center or the edge of the galaxy, versus if I'm looking at somewhere else, up or down, I know that I'm not looking at our galaxy. I can still see it, but I'm not you know directly observing it. Okay. So take a look at our local sky. So we have objects usually in the in the sky, and I say night sky because in the night we can see things, but it's true for even in the day. It doesn't really matter. So we have altitude, which is telling us how high it is from the horizon, an object, and we have, um, you know, the direction of it. Is it southeast? Is it northwest? What is it? So altitude, for example, for this particular object here, or the sun in this picture, it is 60 degrees. Okay, so 60 degrees, and its direction is southeast. So if I want to tell you where the object is, I can give you the direction saying that take a look at the southeast, and also take a look at the altitude of 60 degrees. Okay, this altitude can also be zero. If the altitude is zero, then you're technically looking at your horizon. The maximum it can be would be 90 degrees, that you're directly looking above your head or overhead. This is called zenith. So every time that you see a word zenith, it means an altitude of 90 degrees, or it means overhead. So overhead means zenith. Okay, that's what it means. And there is an imaginary line that starts from south, goes all the way to zenith, and goes all the way to the north. That's an imaginary line all the way from south to north, which you can see it in this picture. This is called meridian. Okay, we use these usually, especially for amateur astronomy, to kind of identify the objects in the night sky. But if I give you an altitude of 60 degrees and a direction of southeast, this is not the best way to give you an address. There might be a couple of stars close to one another. There might be a couple of little objects close to one another, and it's very difficult to identify these objects using altitude and direction. So that's why astronomers think about other ways of addressing this issue, and I'll talk about them. So as I said, zenith is the point directly overhead. Horizon is all points 90 degrees away from zenith. So the zenith is up here, horizon is 90 degrees away. And meridian is a line passing through zenith and connecting north and south pole. Now, if you ever wanted to find the objects in the night sky and you wanted to know how far away they are from one another, you can kind of use some techniques, and I'm going to introduce that to you. So we measure things in the night sky, or to find them relative to one another, we use degrees. We never use miles, we never use kilometers. We use degrees because we see them in the celestial sphere. Okay, so when you're looking at a night sky, these two objects, for example, they look to be at the same distance, but they are away from one another. And the way that we can measure how far away from one another they are is to use degrees. And there are some techniques for that. The distance of moon, the diameter of moon here is half a degree. Your finger, okay, is 1 degree. From your thumb all the way to your pinky is 20 degrees, okay? And this is if you are holding your hand in an arm length, okay? If you're holding your hand in an arm length, then from your thumb all the way to your pinky is 20 degrees and your index finger is 1 degree. Um, your fist is 10 degrees in that situation. So this is one of the ways that you can kind of measure how far away things from one another. If you're in a southern hemisphere, the Southern Cross, all the way from this star all to this star, this is also very famous um, in the southern hemisphere. So this is 6 degrees. If you're looking at the Big Dipper, which is pointing towards the Polaris, these two stars are 5 degrees from one another. So these are some of the techniques that we, or astronomers sometimes use to set up their telescope or to find objects in the night sky. If I'm telling you, okay, how far away these two stars are from one another in a night sky in units of degrees, you can kind of compare them to the diameter of the moon as it's appearing to you, and you can say, okay, so this is the double of that, so it's 1 degree. They're 1 degree apart from one another. Again, this is not an accurate way of doing it. I will introduce an accurate way later on. And we also find out that the degree is not really that detailish. It's not really sufficient. So we started to think about maybe a little bit, we need a little bit more precise. So we decided to divide that 1 degree to 60 equal parts and calling every single one of these 1 arc minute. So 1 degree is 60 arc minutes. Okay, that is if I am taking 1 degree and dividing that to 60 equal parts, one of those parts is considered to be 1 arc minute. If you take one of those, if you take 1 arc minutes and divide that to 60 equal parts itself, that is called 1 arc seconds. So again, 1 degree is 60 arc minutes, and 1 arc minute is 60 arc seconds. Another thought question. Again, please pause the video, read the question, and try to answer it, and then I will go over the answer. So, the angular size of your finger at arm length is about 1 degree. Yeah, we know that. Arm length, 1 degree. How many arc seconds is this? So we want to know how many arc second is 1 degree. Okay, so we know 1 degree times 1 degree is 60 arc minute, and 1 arc minute is 60 arc seconds. That means it is 60 times 60, which is 3,600 arc seconds. It's actually very useful because if you have the angular size of the stuff, if you have the angular size as they are appearing to you, okay, for example, if you have the angular size of the moon or you have the angular size of any object, then you can actually find its physical or actual size. Okay, so angular size, we know it. Physical size, we don't know it. 360 degrees, no problem. 2 pi, no problem. And its distance to us. So if I know the angular size of an object as I'm seeing it, and I know its distance, which we usually show it with r, then I can, using this formula, figure out its actual or its physical size. So in this equation, we know everything except physical size. So it's very useful. Knowing an angular size of objects in the night sky is very, very useful. If you know how far away they are, then you can easily find their actual or physical size. Now, again, one of our goals was at the beginning of our video, we say, why do stars rise and set? And that's exactly where we are at. So if you're looking at this, the celestial sphere is rotating. Where is it rotating from? It's rotating from west to east, right? So west, east. It's rotating from west to east, okay? So that's why we see everything else in the night sky in the celestial sphere rotating in the opposite direction, okay? That's why we see that this is the path of some of the objects. That's why we see this is the path of some of these objects in the night sky. Because we are rotating from west to east, so we see that the night sky is rotating east-west. Okay, so this is north celestial pole, and this is south celestial pole. Now, why am I bringing this up? Because here we have a star on a north celestial pole. We have a star, and that is called Polaris or Polaris star. Okay, and it seems like when you're looking at the night sky, it seems like that everything is rotating around that point. If you have a star here, it feels like that this star is rotating around this constant non-moving object. It feels like this star is doing the same. It's rotating around this axis. So if we record the motion of the stars in a night sky, this is what we would be able to see. Okay. This is where the Polaris is, or the polar star. It's always towards north celestial pole. It's always towards north. This is one of the stars that has been used for centuries by people to know where they are going. Okay, because nowadays we every time we want to go somewhere, we just plug the address in our GPS and we should be fine, right? But imagine 400 years ago, 500 years ago, a century ago, people didn't have these type of things. Okay, if you are out and you are lost, you have to be able to find your way, and that the Polaris was one of the ways that they could find us. So if you're aiming towards the Polaris, technically you're moving towards the North Pole, so you can find where the east, west, and south is. Okay, so it seems like that everything is moving or rotating around this point in the night sky. So if you are here, okay, so that would be your zenith or the point overhead. Okay, the meridian would be an imaginary line going all the way from zenith to the North Pole for you. This would be um, uh, this would be the exact reason why you see some of the stars and why you don't see some of them and why you see some of them rising and setting. So this is star up here. It will never set. What it does, it's just going around every 24 hours, going back to where it is. It is always above your horizon. So this is where your horizon is. If you're standing right there, this would be your horizon. Okay. So this particular star is always above your horizon. It will never set, it will never rise, it's always up there. It's just rotating around the North Star or North Celestial Pole every 24 hours, once every 24 hours. Okay? Now, what about this one? What about this star? This star, no matter what time in a day, it's always below your horizon. You will never get a chance getting a chance to see this star because it's always below your horizon. You cannot see below your horizon. Where's the horizon? It's 90 degrees away from zenith or exactly overhead. So you never get a chance to see it because it's never rising. However, there are stars out there, okay? For example, let's say that this one is a star. It's rising and it's setting. So this is the point that it's rising, this is the point that it's setting. So you get the idea now why we do see some stars rising, some stars are setting. That is exactly why. Depends on where you are on Earth. So a thought question. What is the arrow pointing to? And we just talked about it. Is it zenith? Is it the north celestial pole? Is it the celestial equator? The answer is it's north celestial pole, where the um, polar star or Polaris is. Okay, I'm gonna stop here for the first part, and we'll continue with part two. Stay tuned.